Morning. Today we're going to look at or introduce the next part of our unit, the logarithmic function. What is it? How do we find it? Now we are going to use our understanding of inverses. So we have a graph here, y is equal to 2 to the power of x, and we can fill in this chart. Negative to the negative 3 is 1 over 8, negative 2 4, 1 half, 1, 8, 6. So a very quick sketch of this. I'm not going to get too wound up about it. Here, 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 there. So there's my sketch of y is equal to 2 to the power of x. Now, if I interchange, I want to graph y is equal to x is equal to 2 to the power of y. That's our inverse. We've interchanged our x and y values. So we're going to do the same thing. We're basically going to interchange the x and the y values from above. Now, this is the way that we're going to write log base 2 of x. So it is the inverse of our function. So what we have here is an inverse. It should be flipped in the line equal to x. And my purple graph does look a whole lot like I flipped my red graph in the line of y equal to x. We're going to talk about that shape here in a minute. Okay, so the graph of y is equal to log base c of x is the inverse of c to the x, where c is some value either between 0 and 1 or greater than 1. Again, we have no basis for negative. We don't define either exponents or logarithms with negative bases, nor with 0 or with 1. And it is reflected in the line y is equal to x, whatever place c. Just like every inverse, we're going to reflect it in that line. Now the domain of our exponential function, we talked a domain and range. We talked about that in the last couple of days. The domain is negative infinity to infinity. The range is 0 to infinity, exclusive. There is no x-intercept. The y-intercept is 0, 1. And we have a horizontal asymptote. I'm going to get rid of that. I just say asymptotes there. We have a horizontal asymptote at y is equal to 0. Again, we talked about that in the days leading up to this. So what we should see, since this purple graph is an inverse of this red graph, everything should change. The domain of one should become the range of the other and vice versa. And we can kind of see that here. The domain of my purple graph is all real values greater than 0. My range, now it's going to go down here all the way down, so negative infinity. And it doesn't look like it's going to get to infinity, but it can. It just takes a long time to get there. So we're going to interchange the parts of this we're going to interchange the parts of this. So the range or the domain of our inverse function is the same as the range of our original function. The range of our original function is the same as the domain of the range of our new function, log base c of x is equal to, or is the same as the domain of the original. There is an x-intercept. That x-intercept occurs at 1, 0. There is no y-intercept. You don't see, it's never going to hit the axis. And now the asymptote, it's not a horizontal asymptote in this case, we get a vertical asymptote of x is equal to 0, or the y-axis. And notice again, I'm using a base here, c. It doesn't matter what c looks like, or what c is, as long as it's not negative, 0, or 1. Now, if you were to graph this function, y is equal to log base 1/2 of x, this would be the inverse of 1/2 the power of x, or 1/2 to the x, or 2 to the negative x. 3 ways of writing that one. Okay, I didn't give enough room here. If you're to sketch the exponential function y is equal to 1/2 to the x, you're going to get a graph that looks like that. You can check that on your calculator. If you take the inverse of that one, well, this is going to be flipped down into this quadrant, and this will be flipped up here. What you're going to end up with for the inverse of that is this. But you're still going to cross at 1, 0. The domain is still greater than 0. And you can still see the domain's the same. The range is the same. The x-intercept, you have to take my word for it unless you use technology to do that. There is no y-intercept. And we still have a vertical asymptote at x is equal to 0. So if the base is fractional, or if the base is a whole number, the domain range stays the same. Again, we should have an understanding of the shape of this graph. Now, this is very similar to what we did. Now, you may be able to intuit what this is, but pick a point. I'm going to pick 25 and 2. 25 is equal to log base something of x, or sorry, of 25 is, got that wrong. 2 is equal to log base c of 25. This y is equal to log base c of x. I didn't mess that up. Now, how do you solve something like this? Well, we can figure this out. The power of c that gets me to 25 is 2. So we're actually asking c to the power of 2 is equal to 25. So the power of c that gets me to 25 is equal to 2. We have c is equal to plus 5 or minus 5. That is not a solution to a logarithm. So your base for this guy is c. And you can probably figure that out here without going through that more difficult stuff. So, how do we take this? And this is going back to what we talked about yesterday. The graph is a very simple thing to work with. If you can remember, you do have technology that can help you figuring out the basic shape of the graph if there's a question. How do you do something like this, where you have log base 2 of log base 3 of log base 4 of 64? Work from the inside out. We can figure out what power of 4 gets me to 64. That's 3. Now, we've got this guy. What power of 3 gets me to 3? That's 1. What power of 2 gets me to 1? That's 0. when you have something that's complicated, is that on a homework question? Work from the inside out. Here I'm going to figure out what the exponent is, and then I'll work for what we're doing. The power of 4 that gets me to 64. 3. 4 to the 3 is 64. Now that is an identity. If I have some number c, and I take log base c of x, this answer will always be x, because we have an exponential function and we have its inverse function in the exponent. They are, and as I said, they are inverses of each other. They cancel each other out, and then that's your answer here. If I evaluate log base 2 of 2, the power of 2, that gets me to 2. 2 to the power of 1 is 2. And if you're asked to do something like this, we have different bases, so we can't simplify this at all. Or we can't add them together to start with, different bases. We are going to work with different bases, or similar bases in the next little bit. But all right, the square root power of square root 2, that gets me to 8. That's going to be a bit of a problem. Well, let's take a look at it. Square root 2 to the 1 is square root 2. Square root 2 squared is 2. Square root 2 to the power of 4 is, to the power of 4 is 4. So therefore, square root 2 to the power of 6, square root 2 times square root 2 times square root 2, we have the square root of 64. So a little bit of work, we can figure this out. We can replace this entire statement with 6. Now, power of 9, that gets me to 3. Well, 3 is the square root of 9, so I can replace this entire statement with 1/2. And now we've turned everything into numbers. We end up with an answer of 7. So we have to work methodically through this, but it's not that difficult. We're just going to use our understanding of numbers to go ahead and to figure out what the answers are for each individual logarithm, and then add together. Now, we're going to, and I apologize, my calculator is not working on my board, but we're going to talk about how we can do this. Now, we can't do log base 2 of 2, or of 50, I should say. Log base 2 of 50. In our heads, we can't do it. We can estimate it, but we can't get an exact answer. What I do know, log base 2 of 32 is 5. 2 to the power of 5 is 32. So I also know log base 2 of 64 is 6. So somewhere in there, this answer is going to be somewhere 5. Well, I'm closer to 64 than I am to 32. I'm going to take a estimated guess at about 5.5. So we can't determine this log base 2 of 2, log base 2 of 50. We can't determine that right now, but we can get an estimation for it. And my estimation is it's not great. I said 5.5. I got 45. So my estimation could be better. So I probably should have put 5.6. So that's how I would estimate it. But let's see if there is a way, obviously, that we can use technology. We could have at one point used a bunch of tables, but we all have calculators now. Now, there are 2 types of buttons on our calculator that are useful to us. There are common logarithms, which are basically base 10 logarithms. Now, they're called common because they're used so often. We count base 10, we tend to use base 10 for logarithms. So for example, log base 10 of 1,000 would be written as log of 1,000 with no base down here. But we still interpret that the power of 10 that gets me to 1,000 is 3. So log base 10 of 1/10 is most commonly written log of 1/10, and that's -1. So the common logarithms, that's a button on our calculator. It is next to the 7. And anytime you see, if I was to write log of 7,023, what I'm asking you for is log base 10 of 7,023. Now, the other one, the other tool on our calculator is the natural logarithm button. And Euler's number is an irrational number, like pi, 2.718. This number, there it is right there. This number shows up quite often. And the reason why we use natural logs has to do with graphing and has to do with calculus. When we take the derivative, which is a terminology that we use later on, we take the derivative of a logarithm. That's a complicated one. But if you take the derivative of a natural log, life becomes a lot simpler. The derivative of natural log is 1 over x. And that's one of the reasons why we use this a lot in calculus. Now, what you're going to see if we do natural logs, and we're not going to use them much in -1 math, but if you see ln5, what it means is log base e of 5. So we're taking this log base e, and instead of writing that, we're writing the ln. Same thing with this. Log base c of 16 is written to be ln 16. This is a very, very common tool. You almost never see base 10 or base 2 logs in calculus or a higher level calculus. Now, these guys here, again, I wish I had my calculator on my computer, but I don't. So all I'm going to do to punch in all of these guys is I'm going to use the button that's next to the 7. I know it's hard to see, but right next to the 7, there's a button, and all you do is go log of 500, hit enter, 2.698. So again, what this means is 10 to the power of 2.698 ... is 500. ln 35, same thing. I'm going to use the button which is right below the logarithm button. I'm just going to go ln 35, and this answer is 3.555. So what this means is e to the power of 3.555 is 35, and so forth. Log 16, 1.20, or ln 1/5 is -1.609. So that means e to the -1.609 would be R1/5. Now, there is buttons on our calculator, and if you go to your math tool on an 83, an 84, and if you scroll down, you will find something that's called log. You will see log base. Okay, so if I was asked you to do log base 2 of 50, we would use that log base 2 of 50. So we would, depending upon which calculator it is, sometimes you'll be given log of this, and you put the 2 here and the 50 there. And sometimes, depending, as I said, depending on the calculator, you may have to go full 50, 2. What we're looking for, the base that we're looking for in. And once I get my calculator back, or I will show you some different ways of doing that. But those of us that have older calculators, those of us that don't have access to a scientific calculator, well, maybe not a scientific, we don't have access to these calculators that do the work for us. They only have log, base 10, and natural log. Now, if you use your calculator to do this and you go log 25 divided by log 5, don't have to do that. Log, well, we guess we kind of do. This is equal to 2. Because we don't know what power of 10 gets you to 25, what power of 5 gets you, or 10 gets you to 5. When you use your calculator and do that with logs, we get 2. Now, if we evaluate log base 5 of 25, the power of 5 that gets me to 25, we know that answer to be 2. Now, using the natural logs, we're going to do the exact same thing, and we're going to get the exact same answer, surprisingly enough. I know the answer to this. We notice that the answer is the same. Now, let's see if we can do this with one more. Power of 3 that gets you to 243. 3 times 3 is 9, times 3 is 27, times 3 is 81, times 81 times 3 is 243. So that answer, power of 3 that gets you to 243 is 5. Now, using our calculator, if it holds true, and it does, if I go log 243, making sure I close my brackets and divide by log 3, I know it's very boring for you to see this, we end up with 5, and the same thing for our ln. But not surprising, as I'm doing it, you probably notice that it's going to be the same. How would I evaluate log 4 of 64 if I didn't remember this? I would punch this into my calculator as log of 64 over log of 4, or ln of 64 over ln of 4. This is one of the properties of logarithms. Okay. So what this leads us to is one of the identities which is true for any base and any number. Power of b that gets me to c. If I don't have that log button on our calculator, I don't have log 2 or whatever, I can write this as log base a over c over log base a of b. So basically, whatever base, we tend to use 10 or base e, but we can also write it for any number. We could talk about base 2, base 6, whatever. But more, like we're doing this on our calculator, we want to figure it out. Basically, we use 10 or we use e. So if I want to calculate log base 5 of 221, and I have only a calculator, let's say I have my phone. It has a log button, but it doesn't have the log base button. I would have to punch this in as log base 10 of 221, and I'm going to divide that by log base 10 of 5. Okay. So we end up with an answer of 3.325. So that's 5 to the power of 3.325 is equal to 221, approximately, because I've truncated my answer. Now I'm not going to punch these into the calculator because you're going to be bored looking at me doing it. But here we have log base 2 of 1 over 1,000. Now, I almost always use log base 10, but there's no problem with me or with you using the natural log button. Take the natural log of 1 over 1,000 divided by natural log of 2, or log base 10 of 1 over 1,000 over the common log base 2.
and continue on. The only thing that you would do differently here is you would leave the 3 out in front. Log base 7 of 512 over log base, sorry, that's not right. Log base 10 of 512 over log base 10 of 7. And our final one over here, natural log of the square root of 1 over 1024 is equal to the natural log of 2, or over the natural log of 2. That one you can actually do without, you can work it through it without having to use your calculator, but this is how I would punch it into my calculator if I was using my phone. I would basically, if I'm using my calculator, I probably am going to punch that exactly in, and I'll show you that once we get back. So, if you get a chance, take a look at, maybe do some of these questions. I'll go over them when we get back into class. Have a good afternoon.